If you could survive the crushing gravity and insane radiation, what would the final moments of a plunge into a black hole feel like? Would you be instantly incinerated by unimaginable heat, or would you freeze solid in the ultimate cosmic vacuum? The reality of entering a black hole is far stranger than anything Hollywood has ever imagined, playing out a terrifying cosmic drama of heat, cold, and infinite pressure. What truly happens to a space traveler who crosses the point of no return? To answer that, we have to track the terrifying temperature you will encounter on this insane journey. From the swirling mass of the accretion disk surrounding the black hole to the edge of the event horizon, all the way to the crushing zero point at the very heart of the abyss, or what we call the singularity. The journey begins not with darkness, but with blinding, searing light. As our hypothetical traveler approaches a typical feeding black hole, one that is actively consuming matter, they must first navigate the accretion disk. This isn't the black hole itself, but the massive swirling cosmic traffic jam of gas, dust, and plasma that the black hole is pulling in. This material does not fall straight in. Instead, it spirals violently around the core at nearly the speed of light. The immense gravitational forces and friction compress and heat this matter to millions, sometimes even billions of degrees. The accretion disk glows intensely, emitting lethal radiation, including X-rays and gamma rays. If our traveler tried to pass through the black hole's accretion disk, they would be instantly vaporized by the thermal energy and incinerated by the radiation, long before they ever reached the true edge of the black hole. The radiation output from a typical active accretion disk around a black hole can be thousands, hundreds of thousands, even millions of times more powerful than the total energy output of our sun. The heat in this outer region is truly astronomical, up to 100 million degrees Celsius. In the corona region of the black hole, temperatures can reach billions, even hundreds of billions, of degrees. However, if our traveler is lucky enough to approach an isolated black hole, one that has consumed all nearby matter and is drifting alone in empty space, the thermal environment changes drastically. Here, the temperature you would experience is incredibly cold. This leads us to the boundary of no return, the event horizon. The event horizon is the point where the escape velocity is equal to the speed of light. Cross this line, and you can never return. Paradoxically, the black hole itself is one of the coldest objects in the universe. Theoretical physics, pioneered by Stephen Hawking, suggests that black holes emit tiny amounts of energy, known as Hawking radiation. This tiny emission gives the black hole a temperature, but it is extremely low. For large supermassive black holes, like the one at the center of our galaxy, the Hawking temperature is only fractions of a degree above absolute zero. That's about minus 273 degrees Celsius, also known as absolute zero. As you drift toward the event horizon of an isolated black monster, you would be falling into an environment dominated by extreme cold, passing through a near-perfect vacuum. Now we reach the moment of truth, crossing the event horizon. This moment is defined not by temperature, but by gravitational force. For smaller black holes, those under a few 100,000 solar masses, the gravitational pull changes violently between your head and your feet. The resulting tidal forces would tear you apart or spaghettify you long before you ever manage to cross the event horizon. You would be stretched vertically and crushed horizontally into a stream of atoms while still technically outside the boundary. A fiery death caused by gravitational pressure, not heat. But if you are plunging into a gargantuan supermassive black hole, 1 million of times the mass of the Sun, the event horizon is so vast that the change in gravity is more gradual. For a brief, terrifying moment, you could cross the event horizon intact. Inside this boundary, the external universe would instantly disappear forever. But what about the temperature inside this dark realm? Inside the event horizon, the environment remains dominated by extreme cold. The initial energy from the outside universe cannot follow you, and the sheer volume of the supermassive black hole's interior means there is very little ambient energy or friction to generate heat. You would be falling through a freezing, lightless abyss. However, that cold environment is temporary. The final, inescapable destination is the singularity. And this is where the rules of physics break down entirely. The singularity is the black hole's true center, a point of infinite density and infinite space-time curvature. It is not heat in the traditional thermal sense that destroys you here, but infinite pressure and energy density. All the mass that formed the black hole and every particle that has ever fallen in is crushed into this zero-volume point. As you fall closer to the singularity, the tidal forces would become absolutely insurmountable, violently tearing your body into its constituent particles. At the singularity itself, the energy and pressure are beyond comprehension. The entire journey, from the scorching external disk to the freezing cold inside the horizon, ending in the 0 point of infinite pressure at the singularity, shows that the black hole is not just a vacuum of light, but an unparalleled paradox of physics. You wouldn't be able to escape the crushing gravity, proving that sometimes the coldest, emptiest places in the universe contain the most terrifying forms of energy. The reality is, temperatures inside and surrounding a black hole vary from 100 million degrees Celsius to near absolute zero. The chance of a living biological entity surviving a journey into a black hole, regardless of its size, is 0%. A black hole represents the most extreme environment in our universe, and the idea of ever being able to tame one is an idea based on 100% fiction.